Welcome to the Frontline Innovation for Resilient and Effective Firefighter Technology virtual series. This is a one of three-part series that we're going to talk about later. But we've also called this new series FireTech. My name is Cody Gould. I work here at the Translational Health Research Center at Texas State University, and I'm going to be facilitating today. So as you all probably know, you are fire community members, and your presence is really pivotal for the success of the projects we're going to be talking about today. Dr. Damian Valles is an associate professor within the engineering department here at Texas State University. He will be presenting to us today. Dr. Valles is also a faculty member or a faculty fellow within the Translational Health Research Center, which essentially means that the work that he is doing is being done in a way that is enhancing connection between academia and our community to make sure that we link what we're doing here at the university with the community out there. Without further ado, I can pass it to Dr. Valles to get us started.
So I just wanted to make sure to share my slides real quick, and I'm assuming you can see them. Thanks so much, Cody, for that intro and everyone who's joining us and the introductions from you guys. Again, I am Damian Valles. I am an associate professor here at Electrical Engineering program at the Ingram School of Engineering. Basically, what I want to talk about is how these technologies, either in robotics, drones, and how artificial intelligence can converge basically to help, again, the safety, the search and rescue and monitoring in fire responses from residential to wildfires to even chemical and industrial, right? And so I'm wearing different hats, THRC fellow, like I was introduced. I have my own lab called the Hype Research Group. I'm the director of that lab, and I have my own outside interest with Firefly Robotics that deals with this type of technology as well. And I'm in charge of working on the research and maintenance of these type of technologies and the development of these things. And I want to introduce basically our observations. Sadly, I think based on the call, it would be the assumptions, right, which could be part of what we started up with, but it's certainly not in the point of view of what we know as a firefighter, right? That's the first thing. We trying to perfect the technology before we can actually even test pilot some of these things. But I wanna basically introduce things that are our goals into developing this type of things and then figuring out if it works, right? Part of the research is not just knowing the needs, but actually figure out what is the things or all the components that are required to make anything ideal happen, right? From data retrieval to dealing with high temperatures, which is a problem for electronics, for the lack of sensors to having too many sensors, and the conditions of a disaster, right? If it's too windy, if the environment is not favorable for these technologies, and all the considerations we have to do. This is just to figure out if the technology even works, right? And we have to figure out how to integrate these things and then figure out the operations of this technology moving forward. So for those firefighters in the call, I think you guys have seen this many times, right? This is a residential fire. This is actually a video from a friend of mine from High Point, North Carolina. One of her neighbor's house is on flames and no one's injured. You can see the chief and the crew working around the house. I'm assuming this is a lot of standard procedures. You would see about 4 to 5 different trucks attending this emergency. And, no one was hurt. Everybody was accounted for once the crew got there. But the immediacy of what I show this video for is the difficulty of the environment, right? So what I like to introduce to the general public is first, the difficulty of when something's on fire, right? The environment changes, the temperature changes. You can see all the trucks in the back. You can see how they're analyzing the situation and how they're addressing the fire from the latter, right? And we're looking at different perspectives of what's going on. When something like a residential fire, it looks pretty dark, visibility is low, and there's a lot of people in walkie-talkies trying to figure out what's going on, right? And so part of what technology can address in this type of situations in real time will be very useful to figure out the engineering behind this. So one, right, some of the things that it's important to know is what kind of data you would get if you were to send technology on this, right? People in walkie-talkies in the video are looking for more information, or they're managing people, or they're coordinating certain efforts because there's protocols involved, there's situations that come up. And we want to make sure that that kind of information can be sped up a little bit more for those who need to make those decisions, right? Technology can provide a solution where you can come in, deploy, and obtain that information without having to risk the safety of those who need to address the situation, right? And understand the situation better. And through the air, through the ground, different technologies can help you capture that data, right? So it's all based on what you end up capturing. And whatever you capture, then you can actually deduce and make the right decisions for that moment, depending on the situation you're in. But then the engineering has to be part of how you consider all those things together, right? So the point here is, like in layman's terms, is that something's on fire. Ideally, what you want is somehow the building or the structure on fire is actually giving you data, right? And if that data travels from that burning structure to the truck, somehow magically happens, people in the truck understand the situation better, either before they get there or at the moment they get there, right? So for now, our limitations in technology would be, in a sense, well, we can fly, we can drive. There's no other magical way to get information except go and fetch the information, right? And drones and rovers could make a possible case in the sense of, well, these things can actually capture different types of data at the same time. They can speed up the process a little bit more. They can provide multiple points of view instantly. And they could handle, if designed correctly, engineered the right way, handle the environment in which they're in, right? Which is part of the research that we look into when we're dealing with these types of scenarios. So part of the things that we have considered, and this is what you're seeing in the video, is basically an augmented reality of us doing a real-time monitoring. If you were to have a rover going into a burning building, right? Can we see the live camera of that rover at the same time and understand what the temperature and the environmental factors are once the rover's in the building, right? And so we're showing you somebody wearing a HoloLens from Microsoft, and then you can see in real time, and you can see my other students walking around the lab. You can see in real time what's going on, understand the environment situation. You can see what the rover sees for navigation, and then we can interface all these pieces of technology. Instead of you having to deal with that, you can see this while you get into the site, right? And ideally, this would give you an insight right away to plan what exactly you need to do by the time you get there, right? And having that kind of information in real time, even managing the rover in real time, will help you do this quite a bit. So we started from a very weird point of view. We wanted to see if there was a way artificial intelligence can help us go through different things. The reason we started there is because the problem is difficult in the data, right? That doesn't mean that we couldn't start with the robotics. It just means that the data itself is so scarce that we needed to understand if this was even doable, even to integrate something like artificial intelligence. Right? Detecting people inside of a burning building is an issue. even listening to people inside when everyone's screaming, or there's a lot of people talking, or there's, fire makes noise, windows break, there's other things burning that creates more noise. And so can we locate people in a burning building? Can we transmit that data? Can we develop the communication that transmits data? And so we started from the inside out, right? We wanted to see if the AI was actually doable. And what we proposed to Dell Technologies about 4 years ago is to figure out the AI in where we can basically put a rover together and put sensors where we're trying to figure out if people can be seen through infrared cameras. Can we actually locate and triangulate people screaming around the building and then listen for that cry of help and then pinpoint their location in the building, right? And so what we wanted to do is not just put the sensors in there, but have the AI change the navigation of the rover to go and find the person that it was either visually detected or it was triangulated in a certain position within the structure, right? And then at the same time as those things autonomously happens, we need to make sure that that data actually gets transmitted to the person in the truck, right? They need to know what's going on in real time and then be able to manage that data going in there. So Dell was one of our sponsors initially that helped us deal with the AI development of this and implementation of the rover itself going through that. And this is an example of why we need to do infrared, right? You can see the smoke on the left. You can see what happens when you go through an infrared camera on the right. And in the visual and the capabilities of technology, in a visual sense, it's just much better with more information. And we're not even talking about thermal cameras, right? Because those give you more environmental, but at the same time, a way to also recognize people. And so AI has the capability to deal with this, right? If we develop the software part of things and where AI lives, we can manipulate the autonomous either rover or drone to do what would you consider a protocol approach to either maintaining the visual of that person or continue to monitor while already tracked and pinpoint someone who was previously spotted, right? And so there's a lot of configurations to consider, but I think it depends on the situation. But this is an example in why I show people, well, this is the benefits of equipping something like an infrared camera. And the same thing with screaming, right? Sometimes if a person is screaming within the structure that's on fire, we need to understand what it takes to, in the software, what happens once you capture that on a microphone, right? Because the AI doesn't understand what we understand as noise, right? And we have to figure out what exactly makes this thing work and what is looked for a computer when someone screams, right? And this is basically a picture of what a human scream looks like to a computer, right? To put in layman's term, we're looking at the frequency of someone's voice screaming and in time, right? And so the one on the left is what happens when somebody just screams. It's a clean scream, you capture it and it's beautiful and it has its patterns, it has its signature. It's very evident that in human frequency, this is the scream. And if you show this to a computer, it will understand someone screaming. The problem is during a fire, that's not the case. Nothing's clean. Yelling with other noise, environmental noise going on, your screen kind of gets interrupted or it actually gets more blurred out and the computer could have a hard time listening to this, right? So we took screaming data, we added noise at different levels, right? So we call that the signal to noise ratio at different dB levels. And then you can see the scream kind of fading out because it's getting noisier and noisier. So that happens to the human ear, right? If it's noisier, we can't hear somebody in the club talking. Same thing in the fire. So the computer, its job is to still recognize the scream, right? And we wanted to figure out if AI can actually figure this out for us because we ourselves have our own limitations in those emergencies, right? So we ended up doing a lot of techniques that they're kind of old. Some people think of Alexa and Siri. Everything they do to process what you're saying, it's technology that was done way before I was even born. And people don't know this, but I dusted out some textbooks from the 1960s to do this project, and it still works, right? So it turns out that people back then understood the frequency of voices and screaming very well. I'm just showing you what happens when we deduce a screaming into ones and zeros for a computer, and what happens when somebody's talking on the right, when somebody's screaming on the left. And you can see more of a heat signatures of what happens to our voices. And this is a lot of mathematics behind this, but what you need to know is that we can interpret and teach a computer what a human voice and a scream sounds like, right? And that's very critical because even though computers could be smart, they're really not. And we have to really create enough examples for a computer to learn what a screen looks like. So we actually deducted all this data to make sure that it can spot humans in really difficult environments. So the heat map and how they look like in infrared, and then how they actually sound when there's environmental factors like noisier, broken windows, the actual noise of fire, and that kind of reduces the scream or the cry for help. And so looking at different ways of how a conversation sounds like, to background noise, to glass breaking, through alarm sirens actually going through, and then the purple, you can see how someone's screams look like. So we're teaching artificial intelligence how to dissect, classify, and create decision making based on this type of things that we biologically can decompose the things we can hear and we listen to, and basically teaching silicon how to do this in a human level was highly successful. Actually, we were very pleased to show that we can actually put this on a computer and run it, and then put it on a rover, put it on a drone, and actually have a small program like AI kind of do these things and tell us if somebody's talking or screaming. And so what we wanted to do is, for the last 3.5 years already, we have evolved in a way that we wanted to first put boots on the ground, and we wanted to make sure we had a rover that kind of mimic what's on Mars right now, mainly because NASA has shown that these things actually work in very difficult terrains, in extreme temperatures, and without knowing the entire landscape, it becomes a way to mechanically move around things that could be actually on the floor when you're either in a residential structure, industrial structure, or anything that can impede someone's navigation through the structure, right? And so a boogie rocking system has shown that it can actually overcome a lot of things. So we started small, right? So you can see the Lowe's bag. This is how low budget we went, but we started mimicking the mechanical chassis of what this would look like. This is not what we currently have, but this is how we kind of prototyped the concept of things and started testing all the mechanical and electrical computation components that need to go into building something like this. And you can see in up top of the green box, the type of computers that not just move the motors, but also make the decisions with AI in it, right? So it requires very specialized boards that kind of make this kind of decisions. And you can see some of my former students trying to wire this up, trying to figure out how to put joints in there. Even though they're not mechanical engineers, they did a good job in trying to put this one together. And you can see some of the final products of this concept and how we were starting to deal with the wiring, the cameras, the infrared, and some of the computers on top. Have a top view of this. We have 3 different computers on top. that deal with navigation, the screening, the human detection, and the communication, right? So we need to send this to humans to make decisions, right? So we needed all these small computers to make this work. And then you can see some internet kind of cables in there. And that was for us to communicate between computers to make the communication much quicker. And then you can see a small video how we were, I'm sure NASA was doing this before deploying to Mars, but we kind of put something that would mimic some kind of furniture, right? Even though you can't see through the smoke, maybe you can actually still go and navigate through a box, right? And then make sure that this thing actually moves and be able to survive and kind of move. Doesn't have the tilting there to make a good left turn there. But again, it was our initial approach to making this thing move. It doesn't move really fast, but ideally what you want to see is something that goes much quicker than this, probably at a much faster pace or a human walking pace where it can actually go and capture data much quicker than what it's moving there. So the autonomous driving is probably the thing we wanted to make the change in this, because like any Tesla car or any autonomous driving features, they have the LiDAR going so they can see and make decisions in the way it's interfaced with the data. Things that we've done with running things computationally more faster than this, and took away the remote system and make it more autonomous so we can avoid walls going around people and do things like that. And so basically what we did is added some of these LiDAR capabilities to that rover, make sure that we can see what the rover is actually navigating through. Again, this is the favorable part of the environment where it helps you see through the smoke and be able to navigate through any obstacles, walls, doorways, and people, right? You should be able to detect people from there. And so you can see some of our, from 2020, we went to something very, very tiny to 22, which is the video you guys got to see. And then 2 years ago, a year and a half ago, we started making the rover much taller, far more bulkier, and with more computational resources, because we were doing more microphones and we were triangulating. We kept adding more things that we were trying to integrate with software and making sure that this was actually possible. Again, we haven't field tested this. We're just trying to figure out if the technology and the design process can actually be implemented, because it is a tall task for the considerations of all the necessary data that would be useful in that kind of emergency. And so it's been evolving for 5 years now, going to our 5th year in trying to make this rover go with more technology going in there. Now, the problem with this, and it's obvious to anyone who probably has been in high temperatures, that these computers, this type of material will not withstand that kind of environment, right? Because, computers have a very low threshold of being able to turn on anything above 90 degrees Fahrenheit. Computers shut down and they stop working very well. That's why they have a lot of fans, or they live in data centers, because they're very sensitive to temperature, and we have to thermodynamically understand how we're going to keep these things cool if we were to deploy something into a burning structure. So what the rover can do right now is basically capture a lot of the environmental data that where it is, be able to detect people in front and around the rover, triangulate and understand the screening. We do have infrared and thermal vision that's mounted into it, and then LiDAR to understand the navigation better and be able to make decisions while it's moving around. The other thing is we can actually send this data to somebody who can just see what the rover is seeing and capturing, right? And so we have a interface where we can actually see the data live into a computer screen, and then be able to understand what's going on within the structure, either In this case, either via radio, which is a lot of the environmental data is transmitted, or via Wi-Fi, where you need more of a streaming capability to make the video or images actually come in real time, because radio doesn't support, or it takes a long time to send video and pictures through that communication medium. So we have to be conscious of what kind of communication we're going to move forward, because it may not be either of those two, right? I think probably some kind of cell phone technology based, where data and video and images can be actually transmitted through the same medium, and then making sure that everything's secured when you do that. Let me quickly speak about other efforts. So you already saw the student kind of like looking at the screen with his hands, moving the rover with his hands, and then seeing the real time of what a digital twin looks like, right? So we created a digital twin of the rover in order to control remote this a little bit better. And you can see the design process of my student, right? As he was trying to create a digital twin of what the rover looks like in the virtual world. So even if you cannot be on site, the goal of a digital twin is that you can actually monitor the rover even from the station, right? So if you can do that, even though it's on a call and you're in the station, you can still see what the rover's doing and then what the rover is actually capturing. So the goal of a digital twin is to have a digital representation as much as you can in real time to understand the situation on some remote place, right? So utility companies use this to monitor their lines. Many oil and gas companies do this to monitor their own sites, right? So they do digital twin monitoring to make this thing work. And besides generating and developing the graphics for this, you do have to have a way to communicating the thing you're watching, the digital representation, to the actual physical thing, right? And we have to make sure that people who are looking at the digital twin are actually looking at the real data that's being captured by the the actual physical rover. Right. The other efforts has been from rovers went to drones, right? Because the immediacy was that there's a limitation with rovers, right? Especially if the rover's not well designed, or the limitation immediately is that it can only go through the first floor. And in a multi-story structure, that becomes an issue as far as the speed and the need for information, especially during that emergency scenario. So drones solve that problem, right? Because you can fly to exactly where you need to go. And what we're looking at is how to design drones that deal with different needs of what it would actually help you analyze either the top of the structure, the side of the structure at different heights, and dealing with different communication problems. Maybe you need a line of sight, and create drones that have a communication hub to help you relay information better, or figure out how to move rovers to higher grounds to help you capture data inside. But what we started doing is trying to figure out, you can see an example of two of our drones here that are also being equipped with the same type of computers that the rover has. And they also utilize AI to make this work, mainly because we need to make decisions and detections of people through windows. We need to capture the environmental data that it sees, and it needs to self-navigate around a structure, which is something that we're trying to teach a drone how to do without humans remotely using this. So ideally, what we want to develop is a system where any emergency responder goes to a side and just pushes the easy button, and everything self-deploys. When you do something like that, there's a dynamic that needs to be orchestrated, and there's a dynamic of not getting in the way, right? So there's two very engineering aspects to this type of things. And that means that every piece of equipment, like a drone or a rover, will need to have its AI computation on the system, and then be part of that coordination of understanding what its purpose is in that emergency. If you're going to self-deploy, it has to self-come back, right? So that's the other part of the engineering challenge, is that we want to make sure that firefighters do what firefighters were trained to do. And we understand that you're not here to maintain drones either. And we understand that you're not there to maintain rovers, right? So we have to make sure that when we design these type of solutions, your time with these equipment is just so you can check they work or they're fully charged. But other than that, the responsibility of any firefighter should not be to engineer and repair these things unless there's a massive need. But I don't think that should be the job of anyone dealing with an emergency case. And so what we're trying to figure out is how to make this work. But the problem is with the rover and the drones is that the material of propellers and the chassis of these drones are not withstanding of high temperatures when it comes to structures, not necessarily in open air. I'm showing you an example in how we're trying to teach a computer how to navigate through structures within a simulated building inside of a floor, and you can see all the agents, AI agents, trying to figure out with LiDAR how to navigate, how to look for rooms, how to look for people around there. You can see a lot of confusion on the top left of different AIs trying to figure out what's going on. And you can see one that's really smart and curious, and it's actually navigating through the whole thing. And on the bottom right, I'm showing you the heat map. Once you leave this simulation running for many hours, the AI starts to figure out where it needs to go to search and rescue for people, right? We put 3 different rooms in the middle of the simulation, and then we want the AI to go in there and search for people. And at the end, in the heat map that you can see there, you can see how the AI figured out how to go and do something like a protocol, like go into a room, search if there's somebody else, if not, move to the next room, right? And just kind of quickly do this over and over again and let the AI understand the coordination, orchestration that it needs to do in order to make sure to go into this space and clear it, right? If it's not cleared, then mark it as somebody inside, and then let the people who need to know that and transmit that information. Right, so part of the implementation of this, like how do we move forward from my lab to all these conceptual implementations, AI considerations, all these robotic testings that we've done, is that everything like this will need investments, right? So part of my job as a professor is to get research grants to make this work. What I've been able to do is through the National Science Foundation and THRC, is that I've been able to continue to invest in these type of efforts to understand better how we integrate all these capabilities, right? The robotics is one thing, the thermodynamics to keep it cool is another thing, but also how do we put everything together? It's its own challenge and investment that needs to be done. The investment has been able to come from different places. This idea came from me when I was a junior faculty, and we basically started doing this in trying to figure out how to engineer either new ideas, and mainly the new ideas would be firefighters telling us what really happens and what we should really consider when we're implementing these things. The material, I am starting to work with a material scientist who's helping us making the whole electronics and the material fireproofed. So we're looking at material that can withstand 2000 degrees Fahrenheit for 15 minutes, which is quite an achievement if we can actually sustain that kind of temperature within our drones and within our rovers. and keeping our computers cool at an operational temperature while we're in the middle of the environment. We're looking into new programming because AI is so much changing every other week. Keeping up with the implementation of AI is going to be a challenge, but it's got to be an AI that we can all trust, right? So part of the sake of doing AI is not because we're doing AI for the sake of it, it's because it's an AI that eventually we will have to trust when it comes to serving these type of calls, and then figure out who's going to support these, right? When a drone goes down, or we lose a drone, or we lose a rover, or something malfunctions, I feel like there's got to be a way to maintain this kind of investments and this type of service to first responders, because not everything's fire, but the drones could still be utilized to monitor wildfires, to monitor other situations. We've seen this with police departments. We've seen this with other things. Sadly, we also see it with news channels and broadcasts of people using their drones in a site where they're probably not supposed to. So there's a way to figure out how to support first responders in using this technology without stopping what first responders should be doing and that we're trained to do. Part of this issue is that how do we tackle some of the worst case scenarios like oil rigs, chemical industrial kind of fires? The environment changes from a residential to something like this would be quite a challenge for technology. I do believe that there is a way to get around this, to make drones still viable in providing information on these scenarios. It's going to be difficult, but I think AI and us physically making AI move a drone through either bad environments or really harsh weather, right? We're talking about high winds that may cause the wildfire, right? And then navigating a drone in that environment is very difficult. But that means that we can have AI navigation that can help us have stable drones that can actually go and monitor even when it's really windy. But the hazardous combination of with environmental challenges, it's part of what we try to keep working on in our labs to make sure that we can have a eureka moment where we can innovate on implementation to these drones to be able to monitor these things. And that's part of why I come to work. And so why is this important? Well, financially and economically speaking, I'm looking at, a way of people who can invest or even work in building these things. I think it's not just a one purpose technology, it's scalable to other uses. And I think other people have realized that. I don't think I'm the first one, right? There's other people who are thinking along the lines of drones for many other things. Same thing with rovers. And then figure out how they get deployed. I think the discussion was that how do we relocate these resources from day to day or hour to hour, knowing where some of the warnings are, like wildfires, since we've been in a dry spell, right? And we get those warnings on our phones now, we can actually monitor and mobilize resources in the right places in order to get there quicker. And also create jobs of people who can maintain these, right? From technical to mechanical to programming, to people who have different skills that would need to maintain and keep upgrading the capabilities of this type of technology, just so we can help first responders. And our focus is first responders to deal with these type of technologies, harsh environments, and sometimes crazy weather that presents themselves during the emergency.